Hello, dear fellow listeners and viewers of this channel. This is the second video in the cycle Quantum Mechanics 100 Years of Wonder Magic. We will discuss now at very high level the prehistory of appearance of this science. We can definitely say that the whole story began 360 years ago. Then, in 1666, Isaac Newton discovered that our white daylight is not actually white. Using prism, he split it into components of all the colors of the rainbow. A bit later, about 320 years ago, Newton laid the foundations of a differential calculus. This branch of mathematics is the basis of modern physics nowadays. Then, 250 years ago, Henry Cavendish discovered what he called inflammable air and what we now know as hydrogen. From point of view of modern physics, hydrogen atoms are most simple elements. Looking ahead, let's say right now that each hydrogen atom consists of just two particles, one electron and one proton. Okay, now we skip another century and note now that 160 years ago, Bunsen and Kirchhoff discovered atomic spectra. At first, it was noticed that different chemical elements color the burner flame differently. For example, if you sprinkle kitchen salt on the flame of a lighter, we will see that the flame turns yellow. Or we can dissolve different water-soluble salts in 40% alcohol, then moist cotton discs with them. Next, add 95% alcohol on top and set a fire. We see that sodium ions color the flame yellow, doubly ionized calcium produces red, and boron triple ions gives us green flame. Bunsen and Kirchhoff went further and placed a prism in the path of light from the flame. They discovered that each element produces not just light of one color, but a linear spectrum. Linear spectra are unique to each chemical element, like fingerprints for people. You can easily find pictures with linear spectra of different elements on the internet. But now we are more interested in hydrogen. What is its linear spectrum? In any book on spectroscopy, you will find that the spectrum of hydrogen consists of four visible lines, red, blue, and two violet ones. Some authors call lines differently, for example, as red, green, blue, and violet, or something else. Let's look at hydrogen spectrum by own eyes to check their colors. In theory, I could get hydrogen gas and burn it in a burner flame, but I will not do this for two reasons. First, hydrogen is explosive. Please do not do any experiments with this gas at home, and especially do not allow children to do this. Second, even if I burn hydrogen in a burner flame, I will not see the promised spectrum. We will see the spectrum of hydrogen molecules, H2, but not the spectrum of atoms or just H. Temperature of burning flame is not enough high to prepare atoms able to radiate. That's why I will use special lamp filled with hydrogen molecules. Molecules will be dissociated into atoms and then atoms will accumulate necessary energy due to electrical excitation of hydrogen gas inside the lamp. Then, setting up a prism for video shooting is not easy. For this reason, I will use another device. This will be so-called diffraction grating made at home from a DVD disc. Due to microscopic grooves on the surface, DVD disc can decompose white light into colored components. We can easily see this if you look at the surface of the disc from the side. Note that the prototypes of diffraction gratings were bird feathers. The ability to split light into colors was noticed in the days of Newton and even beyond. Well, now we turn on the lamp and, surprise, instead of four promised lines, we see all rainbow colors. What happens? Where is the promised simple spectrum of four lines? But don't worry, nothing wrong. All four lines are here. This is the red line. One of these two green-blue lines is also ours. Two more violet lines are around here, but they are poorly visible and we cannot distinguish them. And what are the rest lines? What are these distinct lines in the yellow-orange zone? What is the second green-blue line? The answer is the following. In total, the lamp generates not just 4 but more than 2000 lines. We observe a mix of lines generated by hydrogen molecules and atoms and their ions, and also generated by metallic elements of the lamp. Scientists in laboratories also never see pure spectra. I especially demonstrated this experiment to show that reality is usually not as simple as we read in books. It is quite normal to omit even bright, obvious facts to simplify explanations. I also apologize in advance that I omit now and will omit on future presentations many details that some of you, my fellow colleagues and dear listeners, readers, and viewers, may consider important. Nevertheless, the spectrum of hydrogen does have four visible lines. We have clearly seen at least two of them among mixed with other colors. I also pointed to the violet area where two more lines are hidden. What are correct colors of two visible and two more invisible lines, everyone answers differently, and I think now it is more clear why. Now let's continue our story. For a long time it was generally unclear why these lines appear and whether there is any pattern in the location of these lines. The veil of mystery was lifted a little in 1864 when James Maxwell established the theory of electromagnetic field. He also proved that light consists of electromagnetic waves of different lengths. Scientists were able to attribute wavelengths for the four hydrogen lines, but the pattern in their arrangement still remained unclear. There is a beautiful legend about how understanding came. 140 years ago, in 1885, two scientists were working in the mountains of Switzerland. One of them was a mathematician and his name was Johann Balmer. When friends saw a beautiful butterfly, Johann said that he liked to work with numbers and could easily write a formula describing the location of the colored spots on the butterfly's wings. His friend was a physicist. He laughed and suggested a bet. Instead of spots on the wings of the butterfly, he proposed to describe positions of all lines in the spectrum of hydrogen. Surprisingly, Balmer won the bet and described positions of lines with only two integer numbers, n and m. Today we know the more general Rydberg formula, which describes not only the four lines but also all other lines in the spectrum of hydrogen. The formula was found, but why it works remained unclear until new discoveries were made. 130 years ago, in 1897, Joseph John Thomson reported the discovery of the electron. In 1900, Max Planck proposed, and then in 1905, Albert Einstein proved that light is radiated by portions. Today we call such light quanta as photons. The energy of a photon is proportional to its frequency or inversely proportional to its wavelength. 110 years ago, in 1911, Ernst Rutherford discovered atomic nuclei inside atoms. He proposed a solar system model of the atom in which heavy positively charged protons are located in the center of the nucleus and negatively charged light electrons rotate around them. Note that 20 years later it became clear that in general case a nuclei consists of positively charged protons and uncharged neutrons. We have the nuclear industry as a result of these discoveries. But let's continue our story. In 1913, Niels Bohr suggested that electrons cannot rotate in any orbit. Only orbits with certain discrete energy values are allowed. An electron can jump from one orbit to another. The energy difference between the two orbits is carried away as emitted light. The Rydberg formula contains the difference between these energies. So, the energy in an orbit is inversely proportional to the square of the natural number n, which is called quantum number. Quantum numbers for hydrogen are equal to 1, 2, 3, and so on. Now attention, Niels Bohr did not prove correctness of basic principle of his atomic model. He announced quantum rules just as postulates. These postulates laid the foundation for a new science, known today as the old quantum theory. Why old? Because 20 years later it was replaced by a new theory after discovery of the Schrödinger equation. Nevertheless, Niels Bohr made the greatest revolution in physics. This was much more important event than just invention of the Bohr model of the atom. He made revolution in social psychology of scientists and also in the management of science. Did you pay attention to the unusual word postulates applied in his theory? In fact, he was the first who dared to apply publicly and directly a system of axioms to create a physical model similar to how it is done in mathematics. The difference is that axioms do not require any proofs. An axiom is truth by definition, just because it is an axiom. Postulates are a more softer version of axioms. In mathematics, postulates are considered true based on scientific intuition. In physics, validity of postulates is proven by the coincidence of the results between theory constructed with the postulates and experiments. What was important is that old school physicists accepted this approach. As a result, it became possible to announce the most daring high level ideas without the risk of reputational losses or mockery. After Bohr's precedent, a lot of other bold and great ideas were introduced as postulates, including the Schrödinger equation in new quantum theory. But I will tell you about this in next stories. As an epilogue to this video, we can note the following. In 1997, a new atomic element bohrium was named in honor of Niels Bohr. Until now, as of the end of 2023, no one knows what an obvious or intuitively clear driving mechanism or a proven fundamental law causes the electron in the hydrogen atom to have the discrete energy described by the simple formula.